Fort Randall at Cold Bay was officially closed as an Army post on December 1st, 1945. The installation was later deactivated and abandoned in 1950, while Cold Bay's airfield continued in other roles and, in its remaining military form, was not fully closed out until the U.S. Air Force shut its facilities there on July 1st, 1954. Located on the Alaska Peninsula, about 630 to 640 miles southwest of Anchorage, this facility represented a massive and remote logistical footprint. The primary constraint defining this location was its absolute isolation from mainland supply networks. Work at Cold Bay accelerated as equipment and personnel began arriving in December 1941, often under civilian cover associated with the Blair Fish Packing Company. The camouflage was meant to mask a rapid buildup as tension rose in the North Pacific. By mid-1942, the field was operating and the Cold Bay Naval Airfield was formally commissioned on July 14, 1942. Major permanent construction reached completion in early 1943, and expansion work continued afterward as the site added runways, hard standings, and support areas. With no road links, the military hauled in steel, concrete, and heavy machinery by sea along rough, weather-limited routes. Over the course of the war, Fort Randall accumulated a vast inventory of aviation fuel heavy equipment and combat aircraft components. Units operating fighter and bomber aircraft required constant material support to function in the harsh environment. When combat operations ceased, the strategic value of the Aleutian bases evaporated, but the heavy inventory remained in place. When demobilization orders arrived, the military command faced a severe operational limit. In practice, the command hit a transport cost abandonment threshold. Shipping obsolete, war-weary equipment and surplus material back to the mainland United States often cost more than any salvage return. Returning bulky scrap from Cold Bay could consume scarce cargo capacity, heavy lift gear, and large amounts of maritime fuel, and post-war inventories showed much of what remained was degraded, incomplete, or not worth moving. The close-out plan focused on speed, clear the airfield and support areas, ship out only what was still serviceable or sensitive, and dispose of the remainder on site to meet closure requirements. High-value items such as sensitive radio electronics and viable weapon systems were systematically removed and shipped out. The remaining bulk inventory was immediately reclassified as disposable waste. This waste included surplus construction material, heavy infrastructure, and large numbers of steel drums associated with asphalt and other petroleum products. The physical environment of Cold Bay enforced its own strict limits on how this disposal could be safely executed. Severe sub-Arctic weather meant heavy earth-moving operations could only occur in narrow seasonal windows. Engineers had a short window before the heavy winter freeze locked the ground, so bulk waste was often buried in large trenches on site. Decades later, these wartime and post-war disposal practices triggered formal environmental action. By the late 1990s, agencies were documenting buried drums and petroleum impacts tied to the former Fort Randall facilities. In 1998 and into 1999, crews excavated a major disposal area and removed roughly 2,100 to 2,300 buried drums. Geophysical surveys in 1999 then helped define additional buried drum features near the airfield so later work could proceed with less uncertainty. This initial mapping phase confirmed that disposal near the airfield had been executed on an industrial scale. In the drum burial area associated with asphalt and petroleum products, geophysical surveys indicated 2 primary burial trenches along with areas of asphalt exposed at the surface. When investigators reported that many drums were tied to runway paving materials, and that most appeared associated with asphalt, though at least one sampled drum was described as containing petroleum mineral oil. The investigation then turned to defining the true footprint of buried drums, drum contents, and contaminated soil across saturated tundra. To conceal the surplus on site, engineers rapidly cut 2 primary asphalt drum disposal trenches into the tundra. Each trench measured approximately 125 feet long by 25 feet wide. This fixed physical boundary created a hard operational trade-off. The total volume of drums, asphalt-related wastes, and mixed debris far exceeded the available cubic capacity of the excavated pits. To fit the massive inventory into this restricted geometry, the base command prioritized rapid on-site disposal of bulk materials that were no longer worth shipping back. Drums associated with asphalt and other petroleum products, along with mixed debris, were placed into the trenches and then buried under backfill. The operational goal was not preservation, it was clearance and abandonment under severe weather and time limits. In a landscape that punished delay, the trenches became a blunt logistical solution to a disposal problem, not a hidden vault of intact aircraft. Modern environmental remediation at Cold Bay operates within these documented facts. The priority is the removal of buried drums associated with asphalt and other petroleum products and the management of contaminated soil and debris that can threaten water and habitat. The cleanup planning relied on mapped trench boundaries and controlled excavation rather than blind digging. A removal action at the drum burial area was later completed with large quantities of drums, asphalt, contaminated soil, and debris taken off-site for proper disposal and management. The work treats remaining non-hazardous debris as waste material, not as an archaeological collection. How does a mechanically crushed layer of aluminum behave when subjected to modern geophysical sweeps? Overlapping magnetic fields generated by mixed metallic debris severely limit the effectiveness of standard subsurface survey sensors. In 1999, environmental engineers returned to characterize the subsurface hazards. Because blind excavation risked puncturing degraded containers and releasing petroleum products into the water table, geophysical mapping had to come first. The designated drum burial area sat on low, saturated tundra near the airfield, with its key features defined by two buried drum trenches. Above the trenches, one documented surface asphalt feature covered roughly 200 feet by 100 feet. The primary operational objective was to define the trench footprint and the perimeter of buried drums, drum contents, and contaminated soils, so future excavation could target hazards while minimizing unnecessary disturbance. Executing this search pattern required technicians to manually walk the sensor packages across freezing waterlogged terrain in straight parallel lines. The environmental magnetometry was specifically calibrated to detect the distinct ferrous signature of standard 55-gallon military waste drums. However, the unique composition of this specific debris field immediately disrupted the search geometry and the sensor processing logic. The subsurface matrix was not a simple uniform soil medium containing isolated steel targets. The target objects were heavily intermixed with large amounts of ferrous material, including steel drums and other buried steel debris. This created an extreme case of sensor masking. Saturated, conductive tundra could blunt ground-penetrating radar, while dense ferrous debris drove magnetometer readings into broad, overlapping saturation. The engineers could not cleanly separate individual drums from the mass below, so instead of chasing discrete targets, they mapped the anomaly as a whole. By tracing the outer edges of the saturated signal, they defined the perimeter needed for controlled excavation. To increase data confidence and verify the initial boundaries, engineers returned to conduct a secondary extensive survey in 2012. They applied refined mapping software and tighter grid spacing to process the overlapping signatures across the broader survey footprint. Despite this severe and persistent sensor degradation, the surface mapping operation successfully fulfilled its primary non-intrusive objective. The surveyors definitively mapped the full extent of the surveyed anomaly field and locked the exact grid coordinates needed to plan controlled excavation. The environmental magnetometry firmly established the safe operational footprint required for the upcoming mechanical cleanup phase. The survey proved the massive scale of the trenches, even though it could not filter the non-hazardous aviation material from the underlying toxic threat. What did these massive overlapping sensor returns look like to outside observers? Those massive overlapping anomalies on the geophysical grids created a direct contradiction between the physical reality of the site and outside perception. When magnetic anomaly maps show a dense, uniform rectangle of metal more than 100 feet long, it can resemble orderly storage rather than disposal. This represents a classic case of false anomaly interpretation, where signal strength and shape are misread as an undisturbed structure even though the subsurface may be chaotic drums, debris, and contaminated soils packed into a trench. That sharp rectangular footprint directly fueled this civilian aviation myth. Enthusiasts equated the sharp geometric boundaries of the excavated earthworks with the physical dimensions of intact wooden shipping crates. However, this interpretation fundamentally ignored the operational constraints of military waste disposal. When excavation finally ground truthed the anomalies, it exposed what the grids could not resolve: a dense, mixed trench fill of drums, debris, and contaminated soils, not intact recoverable aircraft structures. The strongest returns matched compaction density inside the trench geometry, not preservation. Visually, the contents presented as an interwoven, heavily compacted layer of sheared wings, shattered components, wherein crushed formers, material that could not be rigged and hoisted as a coherent artifact because it would tear apart under its own dead weight. The sharp footprint on anomaly maps had made the disposal look orderly to outsiders, but it was a false interpretation of a chaotic, mechanically destroyed matrix. With structural integrity absent, the team shifted focus to the fragmented metal within the hazardous fill. Beyond the radar footprint, what physical evidence actually remained in the soil? Publicly available remediation records support the presence of buried drums, asphalt-related wastes, contaminated soil, and mixed debris in these trenches, but they do not reliably document specific aircraft types or serial identities within the metal fragments. When environmental crews exposed the subsurface matrix, they described a chaotic field of detached material rather than coherent structures. Heavy scrap and distorted components were interlocked in the trench fill, pressed together among large numbers of industrial steel drums. While the overarching aircraft geometry was permanently absent, technicians successfully isolated specific manufacturing signatures among the scattered debris. These detached fragments possessed enough unique structural characteristics to definitively confirm the presence of both P-40 Warhawk and P-38 Lightning airframes. However, confirming the general aircraft type represented the absolute limit of historical verification. And attempting to map the precise serial numbers or individual service histories of these components was permanently blocked by the physical environment. The Cold Bay ecosystem imposed a severe and active destructive force on the buried material. The Aleutian environment features deep, saturated muskeg. This waterlogged tundra continuously infiltrated the disposal trenches, creating and maintaining a highly acidic subsurface environment. When thin aviation aluminum is submerged in this specific soil composition, the acidic water chemically accelerates the breakdown of the metal over decades. The fragile exterior aircraft skins and the heavily stamped manufacturer data plates were subjected to continuous severe corrosion from the moment they were buried. This active chemical degradation was compounded by the local climate. The ground at the site experiences aggressive seasonal freeze-thaw cycles that continually move water through the soil. As that water seeps into compressed layers of light metal and then freezes, expanding ice can pry and stress the fragments again and again. Over decades, repeated freezing and thawing can further break down whatever thin material survived the initial corrosion. These dual environmental hazards created an unyielding forensic boundary. In standard aviation archaeology, recovering an intact manufacturer data plate allows investigators to link the physical wreckage to a specific factory production batch and a documented military service history. At the Fort Randall disposal site, this essential proof chain is completely broken. Extreme physical compaction combined with aggressive hydrological breakdown permanently erased any surviving identifying marks on the fragmented airframes. Paint layers, stencils, and stamped metal tags were completely dissolved by the saturated earth. The chaotic interlocking of the debris field further solidifies this proof ceiling. Because the original disposal operations mixed all the material together before burial, no single engine block can be definitively linked to any adjacent wing section or instrument panel. There is zero spatial continuity within the trenches. Without spatial continuity, mapping the spread geometry of the scattered parts becomes a meaningless exercise. Consequently, exact serial mapping of the components is entirely impossible. The physical material holds absolutely zero interpretive forensic value beyond simply proving its fundamental aircraft type. Recognizing this hard limit, the environmental engineers officially categorized the remaining aviation aluminum as highly degraded non-hazardous scrap. The engineering teams determined that the fragments lacked any capacity for restoration or meaningful museum display. The structural remnants were simply metallic debris permanently trapped in a state of terminal degradation. With the aviation heritage definitively rendered into unidentifiable scrap, what objective remained for the heavy environmental excavators? Extracting exactly 2,138 toxic drums from a dense subsurface matrix of shredded metal required absolute procedural discipline. The United States Army Corps of Engineers operates under a legally binding environmental mandate. In its FUDS work, funding and direction are focused on identifying and reducing risks from contaminants and munitions-related hazards. Under this approach, leaking petroleum products and contaminated soils are prioritized for removal or treatment, while non-hazardous debris is managed primarily for safety and access. Cultural and historical resources, when present, are addressed through compliance requirements and coordination with appropriate agencies rather than as a preservation-driven recovery mission. The environmental excavation teams initiated the final extraction phase by deploying heavy excavators to open the mapped trenches. Their primary target remained caches of 55-gallon steel drums associated with asphalt and other petroleum products. As the excavators trenched into the frozen soil, they isolated and extracted hazardous containers while trying to avoid puncturing degraded drum walls. Across the late 1990s removal work at the main disposal area, crews reported removing thousands of buried drums from the designated zones. During this controlled extraction, operators also encountered mixed non-hazardous metal debris within the trench matrix. Some observers have pointed to aircraft-like aluminum fragments within that debris, but the public remediation record does not reliably attribute such pieces to specific airframes. Because non-hazardous scrap did not drive the cleanup objective, it was handled only as needed to access contaminated soil and drums, and much of it was managed as inert debris during backfilling and site stabilization. The environmental remediation effort extended significantly beyond the physical metallic debris. Decades of structural failure within the buried steel drums meant that heavy petroleum products had severely compromised the surrounding earth. To completely neutralize this invisible threat, the engineering teams excavated 4,760 cubic yards of contaminated soil from the site. This massive volume of hazardous earth could not simply be moved to another location. Instead, the engineers utilized large-scale thermal treatment equipment. This intensive procedural step required baking the excavated dirt at extreme temperatures to vaporize and extract the volatile chemical compounds. Once the soil was thermally purified and tested, it was returned to the trenches as clean backfill, permanently protecting the local water table from historical toxic seepage. With the targeted chemicals extracted and the soil treated for this action area, the cleanup work achieved its declared objectives for reducing risk at that location. Some portions of the former Fort Randall and Cold Bay complex have been documented as cleanup complete, while other areas have required continued monitoring, maintenance, and additional work as conditions and data evolve. The program's end state is environmental protection, and future work proceeds only when monitoring and data justify additional risk reduction.